Okay, so we're gonna do a pretty important section here. This is finding the area of regular polygons. This helps us find the area of things that we don't have formulas for. So things like hexagons and pentagons and octagons, and we can even still use them for things we do have formulas for, like squares and triangles that are equilateral. So you have to remember that the regular polygon is really a polygon where the sides are congruent and the angles are congruent. So a regular polygon that's a quadrilateral would be a square. All the sides are the same and all of the angles are the same. They're all 90. A regular triangle would be a equilateral triangle. All the sides are congruent and all of the angles are 60 degrees. So in a regular polygon, we have a new piece, and it is called the apothem. So I've got three figures here. The apothem is going to come from the center. So I've marked the center with a dot. Let's actually mark the center with a yellow dot. Here's our yellow dot. That is our center of our polygon. The center actually comes from, if I were to circumscribe a circle about the polygon, it would be the center of the same circle. So this is the idea. The circle is circumscribed about the polygon. So it's around the polygon. So the center of the circle is also the center of the polygon. So we have a new word called the apothem, and the apothem comes from the center of your circle, and it intersects at one of the sides. It creates a right angle and it bisects. So it makes a perpendicular bisector. So your apothem is actually a perpendicular bisector with one of the sides. Now we also have another part in our regular polygon called the radius. The radius is the radius of the circle that is circumscribed about the polygon. So for example, from the center of the circle to the edge of the circle, and in our case, because we are talking about a polygon, we're going to go to one of the vertices. This guy would be called the radius. It's the radius of the circle and it's the radius of that polygon because it goes from the center to a vertex. This is my apothem. So if I go back and look at my other figures, the apothem goes from the center of the polygon and it makes a right angle with a side and it bisects. The radius goes from the center of the polygon and it goes to the vertex. Now that radius actually also does one other thing that I didn't mention. It bisects the angle. So it creates congruent angles. So if this is a 60-degree angle because it's an equilateral triangle, then this little piece would be a 30-degree angle. Same thing happens over here. So my apothem starts at the center and it bisects and is perpendicular to the opposite side. And then it also, the radius, bisects the angle. So in a hexagon, we're doing 4 times 180, because remember it's 6 minus 2 times 180, and then 4 times 180 is going to give me 720. And then I divide by 6 because there are 6 angles. So the whole angle here is 120 degrees, which means if I slice it in half, each little angle is 60 degrees, which makes me a 30, 60, 90 triangle. Same thing happens over here. I get a 30, 60, 90 triangle when I drop the apothem and when I look at the radius. It's just that the angles are in different spots. So these two guys right here are really kind of special, meaning that they end up with these nice 30, 60, 90 triangles inside of them. And so they're really popular for problems with the area of regular polygons. So the area of any regular polygon is given by the formula 1/2 apothem times perimeter. A lot of times it's abbreviated as 1/2 AP, apothem times perimeter. So if I'm given the apothem and a side length, it's pretty easy to do. It's when I'm given these 30, 60, 90 triangles that we really get to put all of our geometry skills to use. So let's try a few practice problems. Okay, so if I have a regular polygon with a perimeter of 18 and an apothem of 4, all I have to do is plug it into my formula. So remember, my formula was 1/2 apothem times perimeter. So this guy is going to be 1/2 of 4 times 18. And you can take half of 4 or half of 18. It doesn't really make any difference, or you can multiply them together and take half of the product. But it's probably easier to take half of 4 or 18 and make it 4 times 9 or 36. So pretty easy when they're given to me like that. So let's make them a little bit harder. So now we're going to find the area of a regular hexagon, and it tells me the perimeter. So I really need to find the apothem. But in order to find the apothem, I'm actually going to need to find a side length as well. So we can start by filling that piece in, and the side length would be 72 divided by 6, which is going to give me 12. So now I'm going to draw a picture to kind of help me until I really understand the regular hexagon and where the 30, 60, 90 triangle occurs. So here's my regular hexagon with a side length of 12. Here's the center of my hexagon. I need to find the apothem. Now I do know that this is a right angle, and I do know that it's bisected. So that means that I'm looking at a triangle with a 6 here. It's half of 12. Now I'm going to drop the radius. Remember, the radius bisects the angle. So we did this before. To find the measure of the interior angle, it's n minus 2 times 180. And since I want each individual angle, I would find that for 6. 6 minus 2 times 180 divided by 6 gives me 120 degrees for each angle. Well, if each angle is 120, when I bisect that, that would divide by 2, and it would give me 60 degrees for this angle, or 60 degrees for this angle, which means this angle is 30 degrees. And the side across from the 30-degree angle is 6, which means that the side that I really need across from the 60-degree angle would be 6 radical 3. Because remember, these side lengths are x, 2x, and x radical 3. So all I do is multiply that by radical 3. That tells me my apothem is 6 radical 3. Now you might find a shortcut where all I did was take this 12, divide it by 2, and multiply it by radical 3, and that gave me my apothem. That will always work in a regular hexagon. So now I know my apothem and I know my perimeter, so I can find the area of this regular hexagon is 1/2 times 6 radical 3 times 12. Now we can do half of 6 or half of 12. Either way, that would give me 36 radical 3. And depending on what the problem says, I can leave it like that, or I can actually multiply it out and get a decimal representation. So that would give me 62 point, and it's a really long decimal, so we're just going to round to the nearest tenth, so 62.4. So make sure you're looking to see how your answer is supposed to be given. Now we also have a fancy formula for the area of an equilateral triangle. You can derive it by doing the 1/2 apothem times perimeter on a regular triangle, which is an equilateral triangle. But I'm just going to tell you that it is the side squared radical 3 over 4. You can also derive it from 1/2 base times height. So if you want a challenge, you can start with one of those triangles and try to get to this formula by manipulating it algebraically. Otherwise, take my word for it. So if we have an equilateral triangle, we don't have to find apothems or perimeters or anything like that. If we know the side length is 4, then all we do is plug that in. So we would say that the area would be 4 squared radical 3 over 4. So 4 squared is 16, and 16 divided by 4 would make it 4 radical 3. And then if I needed to find that in a decimal, I would type that into my calculator, and I would say it's approximately 6.9. So that's a pretty easy formula to use. Now sometimes they'll give you the area, and they'll ask you to solve for the missing side. So let's say our problem instead told us that the area of an equilateral triangle was equal to 12 radical 3. And we want to find the length of the side. So we could do this algebraically. All we got to do is set it up where we're using this formula, and we're going to plug in 12 radical 3 is equal to side squared radical 3 over 4. What's nice is they both have radical 3's in them, so I can cancel them out. Now we're just looking at getting rid of that 4. Remember, we don't like 4's in our denominator, so we multiply. We don't like anything in our denominator because fractions make things harder. So we get 48 is equal to side squared. Then we take the square root of 48, and we can either simplify the radical or we can do it in a decimal. If we simplify the radical, that is radical 16 times radical 3. So that would make this side equal to 4 radical 3. Or if we did that as a decimal, we just did a minute ago, that would be 6.9. And that would be the length of the side. In general, when we are looking at areas of regular polygons, we are going to have to do a little bit of problem solving here. It's not going to be a straightforward problem. I highly recommend drawing a picture. If you're not sure what to do, draw a picture. So when you get stuck, go draw a picture of your problem and see if that helps. If you have any questions, let us know. Thanks, guys.